All right, physics reaction video number 31. Today, I think this is like a lecture. I'm not sure. I did notice in the thumbnail that there's some maybe some images from the web or the book. I might fast forward to that, but let's see how it begins.
Good morning, students. Welcome to our physics online class.
Good morning.
Physics, we are in the 5th unit. It is motion of system of particles
5th unit, seems about right.
and rigid bodies. In this unit, we have learned about center of mass, torque, angular momentum, angular acceleration, then equilibrium and its types, also moment of inertia of different bodies, isn't it? Last class, I told you to learn the two questions, that is theorems of moment of inertia, perpendicular axis theorem and parallel axis theorem.
Cool.
I hope you have learned that question at least 2 times. Write that questions in the notebook.
I like that that little nudge, right? I hope you've learned it. I hope you've written it 2 times in your notebook because it's so interesting. When I was in school, I had a really good memory. I don't have a really good memory anymore, but I remember, I don't think I even wrote down what the homework problems were. I would just see them written on the board, or back when they would write homework assignments on the board, and I would say, yep, I know what they are, and I would go do them, and I wouldn't take any notes at all. I ended up not taking any notes at all because I started to realize, why am I taking notes? I remember all this stuff. I never read my notes. This is dumb. I'm just going to not bother to take notes and just take it all in. And I thought, and I thought it felt great. I felt like classes were great. But I started to notice that I wasn't actually hanging on to concepts as well. And it was this really strange thing where just in through my eyes and out my arm, writing down seems to cement it in my brain. And so this idea of helping students say, come on, I know it's pain, but let's write it down twice and we'll get it.
All right. We will start off today's session. Today we are going to discuss about rotational dynamics.
Nice pointer. Boy, this is zoomed in.
That is, beginning we have discussed the relations among various quantities like torque, angular acceleration, angular momentum, angular velocity. Isn't it? Tau is equal to I alpha, L is equal.
So I would guess that if this is the first time they're seeing this, they don't really think of these as vector quantities, right? So the 3 of these 4 are vector quantities in general. I guess alpha is a vector quantity too. All 4 of these are technically vector quantities, but you can certainly do a lot without really thinking of them as vector quantities and just talking about things rotating, I guess, in the same plane all day long, so that L always, let's see here. I should mirror this thing. If we're going around, right, then L is straight up all the time. Its direction is either up or straight down. And if all you want to know is the magnitude, you're good to go with a lot of this stuff. So I'm curious to see if any vector stuff comes into here, but I'm guessing it won't. But just like I've done before, I might occasionally pause to note that everything she says is easy to translate to the vector version of these things. At least the statements we make. I think the algebra, the calculus gets a lot harder, but it's great if your statements remain usable.
To I omega, etc. In continuation with, we are going to learn the dynamical quantities relations. That is work, kinetic energy, power, etc.
Cool.
Okay. First, effect of torque on rigid bodies.
So it's interesting that she has everything prepared ahead of time. At least it seems like that's what's going on here, right? So it's so interesting to compare that with sort of starting with a blank page and doing it. This is always going to be neater, cleaner, better organized. And so I think that those are the huge advantages of doing it this way. I think that the advantages of doing it on a blank page shows students that, it's stream of consciousness and they can, exactly the amount of time it takes you to write it, you give them the same amount of time to write it. But it's interesting. So when I grade papers, typically what I do is I will digitally annotate them, right? What I found is that I can write faster than I can type, I can talk faster than I can write, faster than I can type. And so what I will do is circle something And then when I do the audio, I'll say, oh, well, this paragraph would actually do better on the next page or whatever. And the coolest way that I found to grade was to read it all the way through once and just make tiny little marks, notes to myself, notes that frankly wouldn't have made sense to the students on their own. So I don't actually give the students that hard copy of my little scribbles, but they're just little tiny codes for me. Read it all the way through, then go back and turn on the screen recorder and walk them through and say, yeah, so you spelled this wrong. Well, that's dumb. But, this paragraph here is really, really interesting, but I wonder if your thesis could be stronger if you use the evidence, from this other page here. So that twice through is very similar to what's happening here, right? So she had to think it all through as she put her notes together, and now her brain is ready for it. One thing I've noticed is that if there's too much of a delay between the notes you write for yourself and when you do the performance, for lack of a better word, then it all kind of falls apart. And every once in a while, you'll see a teacher say, "What was I doing here? I don't remember what I was doing here." And that's that moment when we can show our students our critical thinking skills. So clearly, I'm guessing that she has it all written out here, and I would also guess that this was probably written out not long before she turned the camera on, so that it's really fresh and ready in her brain.
That is, a rigid body which has non-zero torque, non-zero external torque, would have the angular acceleration, where alpha is angular acceleration, I is moment of inertia, and tau is the torque. If there is no external torque, that body produces the angular acceleration. So the relations can be written as tau is equal to I alpha. Actually, the torque in rotational motion is equivalent to the force in linear motion. In the same concept, I explained one more important point, that is conservation of angular momentum. Conservation of angular momentum. Do you remember? When no external torque acts on the body, the net angular momentum.
Hang on, what happened there? We didn't see a shift of the page. Let me just go back. Okay, I want to watch to see how the page shifts, because what I'm curious is whether she's actually using the pause button to orient things perfectly. Let's maybe go back 5 more seconds, and then let's watch how that transition happens.
Conservation of angular momentum. Conservation of angular momentum. Do you remember?
Boy, I didn't really hear a gap in the audio. I mean, I guess she was silent there. That was actually really cool. I mean, at first it seems like these were just images that were being flashed on the screen, and yet her pen seems so real and lifelike. So that's really cool. So that's just tiny little things that teachers do to streamline and smooth out the presentation, I think is very cool. So that was really neat. I think what I might do is I did notice in that thumbnail some images. So I think I want to fast forward to where she's talking about some images. Yeah, here we go. I'm curious to see how she does that. So I'm just going to fast forward to there. Back just a little bit, maybe. Just where she starts to introduce it. Just back up time a little bit more. Oh my goodness. I really love this. Well, anyways, we'll see how she does with the image.
So this is the concept you have to understand from the conservation of angular momentum. Let's see the application of this principle. Consider this example. That is the movement of ice dancer or a ballet dancer. Okay? So when they used to perform the musical routine, sometimes they spin slowly, sometimes they spin very fast. When they spins, they'll be stretching their hands out. Also, they'll be bringing back the hands to their chest. Have you noticed this? So look at this figure. Here, this girl is stretching the hands. Here, this girl is brought close to the hands are brought close to the body.
This image is kind of interesting. So these red arrows are indicating, I guess, the circumference of the circle that this point of the hands traverse, but this one is wider than the feet. So, you might also wonder, boy, does that mean does diameter mean fast? But of course, her feet are going to rotate at the same angular speed as the top. So I guess it is really representing just the circumference. And then they suddenly multiply the number of circles drawn now to indicate speed. That's really interesting. I'm trying to think how else you could indicate that this one's spin is faster. I mean, technically, this arrow here is probably quite similar in length to this arrow here. Now, this one maybe is a little bit broader, but it's not really, I don't think they're saying that the length of the arrow is the magnitude. I think they're talking about like the density of arrows, which is really cool because that's how we do like electric fields and stuff. We use density of lines to represent strength. I mean, this is just some book that she has access to. I'm just kind of caught off guard by the way that it's drawing this. I also thought it was interesting, have you noticed this? And so it's really interesting because that means, in my mind, at least two things, right? One, do you actually do this when you go skating or whatever? Number one. And number two, do you notice it when you see other people doing it? And I think the big difference there is the feeling, right? Like, oh yeah, boy, that really scares me when it happens to me when I pull the mass inside. But it's also fascinating to reflect on what you have observed when you're not in such a crazy frame of constantly spinning and getting dizzy, right? What have you observed? Say, wow, that's really interesting how much faster they go. I mean, if it wasn't for the simple relationship, if ice skaters had to do something else to spin around faster, that would be really weird. Imagine if it took, I was going to say muscles. It takes muscles to pull your arms in. In fact, it's hard to do. But that's all you're doing. You're just pulling in, and physics is doing the rest. Very cool.
Isn't it? So why they are doing this two performance? Here, when the dancer spins slowly, the hands are found to be stretched out. When the hands are stretched out, this girl will be spinning slowly. Okay? And this girl spins faster when the hands are brought close to the body. So faster. When they are doing like this performance, in order to avoid of falling, they are doing this. That is the conservation of angular momentum.
So I'm not sure she's going to get to it, but this is a really, really fascinating problem because the angular momentum is the same. Why? Because there's no torque. Why? Because there's a force, right? You are using force to bring your hands into your body, but they're coming directly into the center of mass, and so there's no torque. There's force, but no torque. And so the angular momentum has to stay the same, which is why you're able to say these two things here, right? That they sort of swap. But it's fascinating to talk about work, right? Because if the movement of the hand is in the direction of the force, you're doing work, which means the kinetic energy is going to go up. What? So it's really, really interesting, right? That the angular momentum stays the same, and yet the kinetic energy goes up. If you were to say, hey, my momentum stays the same, how would my kinetic energy go up? Well, that can happen if the mass changes, right? So P equals mv, and kinetic energy is p squared over 2m, right? Which is a funny way of saying it. But because it's p squared over 2m, the p, if it stays the same, the only way to change the kinetic energy is to change the mass. And we just don't tackle problems with changing mass very often. You've heard me say a couple of times, well, if this was a rocket problem. So rocket problems are where we change mass a lot. And suddenly you're like, oh my goodness, all hell breaks loose. But these problems are so interesting because the analogy to mass, the moment of inertia I, changes all the time. This is a perfect example. When you can manually change your own moment of inertia, suddenly the angular momentum, hey, there's no torque, no way, man, I'm not going to change. But the kinetic energy can change because the moment of inertia is changing. In fact, I believe it's L squared over 2I, right? A direct analogy. So P squared over 2M, L squared over 2I. If I is changing And the eye is definitely getting smaller here, right? L stays the same. So that I is getting smaller, so the kinetic energy goes up. I'm just going to let her go a little bit longer just to see if she talks about that. My guess is she won't, because it's kind of tricky, but let's see.
Kept constant. How it kept constant? When the hands are stretched out, the eye becomes larger. Eye becomes larger in the sense moment of inertia. Moment of inertia becomes larger. The moment of inertia, we know that it depends upon mass into square of the distance. So the distance increases.
Right, that's really interesting. The moment of inertia of a whole human being would have some crazy integral, but every single bit, your fingernail, your elbow, everything contributes an mr squared part. And so really all she has to talk about is the hands or the fingertips to write this very simple expression down. This is not, you can't use this simple expression for the entire moment of inertia of a human, but this is sort of how it goes. And so I love how she's broken it down to the very, very simple that, hey, look, R changes, I changes.
About the axis. So, the moment of inertia becomes larger. Automatically, the spins slow. That is, the girl spins slower. That is, the angular velocity becomes small. Understand? So, stretching of hands away from the body increases the moment of inertia. Thus, angular velocity decreases. So, the spin will be slower. On the other hand, when the hands are brought close to the body.
So just pause just for a second. So there are some people who feel like, man, that was a perfect explanation over here on this image. So that's, she says, so if the hands go out, eye's going to get large, omega's going to get small. It's like the whole story. And to come over here on the other side and say, oh, but hang on, let's do it again. It's overkill, but it's not, right? Like, doing both sides to make sure that all the statements are going to hold together. Let's see, my hands are closer in. Okay, oh, the R is going to be smaller. So the I is going to be smaller. So the omega, right? To put the whole thing together on both ends of the spectrum, I think is super important. Very cool.
The moment of inertia decreases. Decreases in the sense I is equal to m r square. So from the axis, the distance is very small.
Perfect.
So the moment of inertia decreases. If the moment of inertia decreases, automatically the spins get faster. That means the angular velocity becomes larger. The angular velocity larger means the spinning get fast. Have you got the point?
Yes.
That is, when I increases, omega decreases. When I decreases, omega increases. So that the angular momentum becomes conserved. So the performance will be in a fine manner.
All right, I'm just going to stop there. Wow, this is really, really cool. Loved the tiny little things that she was doing to keep the presentation clean and nice, right? The page switches were invisible. The presentation, her own writing was really well organized. Love that. I loved the connection to the old stuff that she was doing. I really like what she did with this image. I mean, you heard me, I was complaining about the image a little bit. It's got some funkiness to it, but that's not her fault, right? That's just the textbook that she's using. And I loved how she very, very carefully worked out the stuff on the left side, the stuff on the right side. I thought that was really, really great. I think these problems are super, super interesting. And I got to say, this idea that eye changing is why this gets so hard. I'm sort of fascinated by that, right? Because the mass changing stuff doesn't really happen until you get to the rocket equation. I mean, occasionally you get things sticking to each other, I guess, but this is very, very cool. All right, thanks everybody. Have a great day. And remember, physics teachers are awesome.